So take an ellipse and an inscribed parallelogram to this ellipse. Here's the ellipse black, the inscribed parallelogram is shown red. So I can choose out of a one-dimensional family which inscribed parallelogram I'm going to take. Let's take this one here, for example. And now I can choose a point P on the boundary of the ellipse. I can place it anywhere. Let's place it, for example, over here. And I'm going to drop 4 perpendiculars, one on each side of this parallelogram. Now, because sides are pairwise parallel, the first perpendicular to this side and the perpendicular to this, say, third side, they're going to be collinear, and the same thing happens with alternate perpendiculars on the other pair of sides. So as I move P, you can see that perpendiculars are collinear in a pairwise fashion. Okay, so this is all expected. This has to do with the particular parallelogram I choose. If I choose another parallelogram, I continue to get the collinearity. Now, here's an interesting phenomenon. This might be obvious, but I just noticed it today experimentally. I'm going to go ahead and connect these pedal points, the feet of the perpendiculars drop from P onto each side of the parallelogram. And I'm actually reporting here the length or the perimeter of this black polygon defined by the feet of the perpendiculars, and also the area of the feet of the perpendiculars. So if I vary the parallelogram, you can see that those two numbers there vary. Okay, both the length of the pedal polygon and the area of the pedal polygon. However, if I keep the parallelogram put and I just vary P, look at what happens. I'm just going to go ahead and animate P's motion very slowly. The area of that varying pedal polygon is invariant over all P. So you can see here that I'm varying P. The shape of this curious pedal polygon is varying. Sometimes it's this wedge, this concave wedge. Sometimes it can become, looks like it's always concave. That's pretty interesting, except when it touches a vertex. However, its area is not varying. If I stop this and I change the specific parallelogram I'm considering, let's go ahead and make it this one. So I've changed it slightly. The area changes, right? So just keep your eye over there. The area is changing as I vary my polygon. However, as soon as I choose one, then the area of the set is distinct from the area of any other set, but it is invariant over all P on the ellipse. I can change the aspect ratio of the ellipse, make it be more eccentric, for example, as so. And of course, the phenomenon is preserved. If I change my parallelogram to this one, the phenomenon is preserved. I have like invariance of area with respect to P. If I make my ellipse become more of a circle, I get the same phenomenon. So of course, this is a phenomenon that is independent of the aspect ratio of the ellipse.